For sections 3.1 and 3.2, I'm basically going to combine the notes to them really closely together because they all reflect around the same topic, and that is being able to produce a graph of a function using first and second derivatives to do so. So I'm going to run over a few things here. Some of the main points here. I'm not going to necessarily read everything you see in front of you, but I'm also going to give you a couple of examples, which this time around is going to make use of Google Forms for you to answer some questions, because since there's a number of things you have to do for a single example, I couldn't use the setup I had been using. Otherwise, Office Mix here would get all frazzled. So when we get to the end of this one, or towards the end of this one, you're going to be given an opportunity to answer some questions on two particular functions I'm going to give you, and then I'm going to have you, then go over, have you try it, and then I'll go over it. So how to go about doing it. So when we're dealing with graphs, I mean, if you're being asked to produce a graph of a function, and sometimes it is a good idea to know what the graph looks like. We want to get you to a point where you can kind of visualize what the graph will look like without necessarily having to throw it on a graphing calculator or anything like that. So knowing which points to look for and knowing which points to plot also helps whenever you're trying to graph the function, because of the fact that, even if you put it on a graphing calculator, if you don't have the window set right, you may not be seeing enough of the graph to make decisions about what it looks like or about any particular points of interest on it. So, and we would like you to be able to produce a picture of that graph without having to calculate a whole lot of points. Just some really specific points that if you plot them and know something about them, you would be able to draw a pretty accurate graph with a minimal number of points that you've had to calculate. So now, two of the things we look for a lot of times are what we would call relative maximums and relative minimums. Basically, for a small interval around that point, it's reaching a highest point or a lowest point. Now, that's not to say that if I go further along the graph, will I reach a point that's higher up than that? Maybe, but we're looking to see where it tops out or where it bottoms out somewhere, because that's where the graph changes direction. So don't necessarily think of this as the highest point and lowest point, even though they use the terms maximum and minimum. Think of these as essentially turning points, and that's what we're looking for, when we look for relative maximums or relative minimum. And the reason why we say relative, sometimes you might see some textbooks say local. It just means that for a very small interval around that point, that's where it's reaching a highest point. It doesn't mean for the entire curve, but just for a really small interval close to the point that we're looking at. So that's why they call them relative maximum, minimum. And I said sometimes they call them local, depending on the textbook and who's stating it. So let's go into this here. No, I mean they're describing what increasing and decreasing is, but we're going to be using a test for that using a derivative, so we're not going to get into this too much. But one of the things that we're going to try to get to is that at these critical numbers, where I would have a critical point, and these critical points are these relative maximums and minimums, the slope is either going to be 0 or horizontal, or it's going to be undefined in some way, whether it's a vertical slope or whether you're reaching a corner point or something along those lines. And that's why we make use of the first derivative to help us with that, because I can identify where a graph is reaching these critical points based off of when the slope of the tangent line becomes 0. And so when the first derivative becomes 0, that's when the slope of the tangent line becomes 0, and therefore I found the x-coordinate of a critical point. So what we've discussed in the previous slide is being summarized here. A couple of things about this. First of all, if I'm looking for where I have a maximum or a minimum, these relative maximums or minimums, or these turning points, or these critical points, whichever you want to call them. Again, different textbooks and different problems may have it listed as something different. You're either going to have a situation where your first derivative is equal to 0, which is going to be more common, or if it's undefined, and that usually means you have a vertical asymptote, or it's a turning point because it's a corner point, and you're always going to have a turn there as well. We also have a first derivative test that comes up from that. I don't like the way that the book states it. I'm going to kind of retranslate it, but essentially, if the first derivative is positive or greater than 0, that indicates that the graph of f of x is increasing, and if the first derivative is negative or less than 0, that's an indication that your original function f of x is decreasing. So they're putting it in terms of these critical numbers here. And the reason why they're saying that is that you do have to have this change in, from increasing to decreasing. There are sometimes you may get a first derivative to equal 0, and it ends up not actually being a critical point. It ends up being, it's still increasing through there because the graph may have been flattening out a little bit, and then, will get steeper again. That happens in some functions. Also, if it comes to close to coming to a vertical, vertical tangent line. So, so you have that change, and we're also going to see is that sometimes if there's inflection points, the x value for the inflection point may cause it to be 0 in the first derivative as well. We talk about inflection points momentarily. We use the second derivative to define those. But so whenever you set a first derivative equal to 0 and you try to find the x values that make f of x 0, you're really looking for possible critical points. It's not really a critical point until you show that there is this change from increasing to decreasing. With concavity, concavity is basically showing you the shape of the curve, which way that the graph is more or less opening upward or curling, or cupping, and I've seen some textbooks refer to it. It's concave up if you see the curl going in an upward direction. It's concave down if it's going and curling in a downward direction. The inflection point is a point where the graph makes that transition from concave up to concave down. It's not as noticeable. I mean, basically, you can kind of tell where it's concave up and concave down, and if it's going from one to the other. Somewhere in between in that region, you're going to have an inflection point, but it's not as easily to discern where that is as it would be a maximum or a minimum point. So, the second derivative test is how we make use of that. And the second derivative, and basically the inflection point is where the second derivative is going to equal 0. A few things about concavity. A straight line has no concavity. Concave up means curling up. Concave down means curling down. So sometimes you may have no concavity at all. So piecewise functions, you may not have any concavity because a lot of the piecewise functions that you've been asked to look at so far have had a lot of linear components to it. So, but our test for concavity and inflection points is, well, if I have an inflection point or a possible inflection point for any x value that makes the second derivative equal to 0. Now, each time I'm looking for these inflection points, as well as going back to the maximum and minimum points, I should always be looking for the y-coordinate as well. We're focused more on the x-coordinates because these tests are what helps generate what those are. But we do have to have both pair of coordinates in the process of graphing it. So the way I would test to see if I do have, if these possible inflection points are actually inflection points, or if I go from a situation where I go from the second derivative being positive, which means it's concave up, and then it transitions over to being concave down, or the second derivative being negative after that. So that's how I can tell I have, concavity changing. That shows me I have an inflection point. It's not as frequent that you'll have an inflection point without or a possible inflection point not end up being an inflection point. It's very rare for that to happen. So don't think it's going to be a commonality you're going to see. Usually if you get an x value that makes the second derivative 0, it's going to be an inflection point. Whereas you may have from time to time an x value that might make the first derivative 0 and not actually be a critical point. So, as this is trying to get to something I mentioned before, what we're going to eventually use is a sign diagram to help us figure out what the graph should look like. Because again, what this is telling you is, being able to do these things and be aware of some of these things also help you become better at graphing functions, whether it be on a computer or on a calculator. Because, most of these programs that you graph things on will start off with a window that's either been predetermined or it's based off of what the last user had set up beforehand, whatever the case may be. And the function you're looking at may not fit well enough on there to see all the features like the maximums and minimums and things like that. So, you'd have to change the graphing window to really see what's going on there and know some things about that function for that to happen. Because sometimes students, you'll have a graph that may do a lot of curves, but I've seen students in the past that would have the window so focused they just see like a straight line portion of it, or what looks to be a straight line. They think it's a straight line, and it isn't. So, again, that's kind of emphasizing why we study this a bit, so you could get better at showing what these graphs look like and knowing what they should look like based off of these behaviors. So let's look at an example about how we would go about graphing a function using the first and second derivative tests to help us. And for example 1, and those I'm going to have you work on as examples for you to try out, are going to be based off of polynomial functions. So you have a cubic function here, f of x equaling x cubed minus 12x squared minus 60x plus 36. I want to find all the critical points, all the inflection points, where it's increasing, where it's decreasing, where it's concave up, where it's concave down. And if there's any other points of interest I might need to have, I can look up those too and be able to graph the thing. So I'm going to find the critical numbers first. Now, critical numbers may or may not actually turn out to be critical points. I have to first see what goes on with them and how the behavior occurs around those numbers. So I'm going to take the derivative first. And when I take the derivative of the function we started with, I end up with 3x squared minus 24x minus 60. So I set that equal to 0, and they're showing some factoring here because they're not showing this setting it equal to 0, but basically if I factor it out. Now, obviously, if it's quadratic and you're not so great at factoring, by all means, either at this point, use the quadratic formula since it is quadratic, or since we're looking at something we do with the first derivative, if you want to use your calculator to find those, whether it's using graphing methods to figure out where it's 0, or if you have one that can actually solve quadratic equations. There's some that have that built-in function. There are some that you could get programs for. On the Texas Instruments site, if you have a TI calculator, you can certainly use that. So they show here the factoring of it being done. They will usually show that because it's, again, something that's easily done if you recognize it, not so easily done if you have trouble recognizing it. But we do get two values of x. It's going to make f prime of x equal to 0, and that's at positive 10 and negative 2. So those are possible critical points. They're in the domain of the original function because the domain for the original function is all real numbers. Sometimes you might be given a function with a predefined domain. You'll just want you to graph it on an interval. If that's the case, then you would throw them out and throw anything out that falls outside that interval because it's a non-matter for that. So I have these possible critical points, and what I'm going to do now is I'm going to make a sign diagram. So basically, it's a number line. I'm going to put the two values on where they're the critical numbers. That's where f prime of x equals 0. And I want to see what the graph is going to do around that. So what I do is I pick some numbers In this case, these 2 points of reference split a number line into 3 sections. The first section is anything less than -2. The middle section is anything between -2 and 10. And the third section is anything after 10. And what I'm going to do basically is pick a value from each one of those regions, and I'm going to plug it into the first derivative. So we're using what they call in the book a test point. So if I look at the factored form there, if I choose, for instance, f prime of -3, now -3 is before -2, so that would hit the far left region. I calculate that out. I get a positive result. I mean, you can actually calculate what the actual number is. They didn't do that here. But if you have it in factored form, you can kind of guess if it's going to be positive or negative based off of just that information. So when you see this here, if I do f prime of -3, I get 39. It's positive, and if it's positive, I know it's going in the upward direction. I know at x equals -2, it's going to flatten out a bit because at least the tangent line is. It's going to round off and reach a highest point here, it looks like, or at least flatten out right now. And I'm going to use another test point. I pick a value between -2 and 10. They use 0 here. That's what I would usually pick. And again, I'm plugging this into the first derivative, not the original function, the first derivative. And this is where you have to be really careful about what you're doing and really be paying attention to what you're doing. I'm going to need to find coordinates for some of these points as we go along. So at -2, the x value, I'm going to need to find the f of x or y value for that x value at some point if I want to graph this thing. So I'm going to need to find that, but right now I'm plugging these values into the first derivative to get an idea about whether or not it's increasing or decreasing. Now here, excuse me, f prime is negative. So I know the graph is moving in a downward direction at that point, where then it gets to x equals 10, it's starting to bottom out and level off again. And then I plug in a value that's more than 10, say 11, and I get 39 again, which is positive, so I know the graph is going to be increasing at that point. So I know the graph is going to be doing something along the lines of, and I'll draw it over to the side here, something along the lines of increasing, decreasing, increase. Now I don't know how far up or down they go. I don't know if the concavity is right yet. For polynomials, the concavity is going to kind of go along with the maximums and minimums to make it a nice smooth curve. But I'm speculating at this point. I'm going to use a second derivative test to figure out if those concavities are right and when I should go from concave down to concave up or vice versa. So the sign diagram we have there is showing that, on the open intervals of increase are from -∞ to -2 and 10 to infinity, and the open interval of decrease is -2 to 10. And that's something they're often going to ask you to identify is what are these intervals of increasing and decreasing. And you're going to see that whenever I do my example as well after you get a chance to add them. So this is what we have from our sign diagram for the first derivative. And so they do calculate the y coordinates at this point. So f -2, I can see it's a relative max because I go from increasing, I level off and start decreasing after x equals -2. The y coordinate's 100, so I have a relative maximum at -2, 100. And I have a relative minimum at 10, -764. And again, these were done by plugging into f. Notice I'm plugging into f on these, not f prime. So again, you got to keep it straight what you're doing, what you're looking for, so you know you're plugging into the right formula. Now to do the other part of the graph to make it even more accurate, I'm going to look at the inflection points and where it's concave up and concave down. So I'm going to look at the second derivative, which is again basically taking a derivative of the first derivative. If I'm differentiating f prime of x, we had gotten that f prime of x was 3x squared minus 24x minus 60 in the previous example. So now I'm going to do the second derivative. I'm going to differentiate that, and I get 6x minus 24. Now again, I'm looking for inflection points here, so I am going to set that equal to 0. And at x equals 4 is where this is going to become 0. So this is a potential inflection point. I'm going to make up another sign diagram, this time for the second derivative. And what you see here is that, kind of just a fast version of what we've done before. X equals 4 is where the second derivative equals 0. If I plug 3 in, I get f double prime of 3 is negative 6. That's a negative value, which, whether you put a little negative sign or you say it's just less than 0, indicates that the graph is going to be concave down. And f double prime of 5 is equal to 6, which is positive, which means the graph is going to be concave up. So before the x value of 4, it's going to be concave down. After the x value of 4, it's going to be concave up. And I need to make sure when I draw the graph, it looks in that manner. So, and the inflection point itself is at 4, negative 332. Now, when you're in the process of graphing, these points that we're finding, we found the maximum, we found the minimum, we found this inflection point. Those are all points that are going to be helpful to me. If you have it on an interval, you should be also calculate the endpoints. If it's not on a particular interval, you should definitely pick a point, that's to the left of your first critical point and to the right of your last critical point, so that you have an idea where to start the graph and where to end the graph and things of that nature. Or at least, so that you have a nice, good-looking graph from that. So in step 3, we now sketch the graph. We use the first derivative sign diagram to know where it's increasing, decreasing, where it levels off, where it reaches maximums, minimums, and so forth. We also use the second derivative, to kind of get an idea what it looks like. Now, this one's only showing the critical points on this. Remember, at 4, negative 4, here's where the inflection point would be. And you kind of see it. I mean, it goes from concave down to concave up, right around there. You see the transition at that point. And, again, this one, we really only had three points. You'd probably want to have another point like over here and over here to make sure you're accurately placing that. But that's a pretty accurate graph. We're only looking at 5 potential points here. So the examples that you have to do on the following page are going to give you endpoints. They're going to say, find, sketch a graph from this x value to this x value. So it gives you a place where they start and end, so that also will give you additional points on the graph to help localize it and so you know where it is. So now you're going to be asked to identify the important points of these functions here. So you're going to be given the opportunity to run the test that I just demonstrated, and you can answer these in play pause it. So pause a moment. Well, the questions will be presented to you, so answer each one, take your time in answering them, and see what you can come up with. Okay. You were asked to find the critical points and inflection points, and ultimately, find all the important, things to help you graph this thing. So that's what I'm going to do with this. I'm going to find not only those critical points and inflection points, but I'm also going to comment on where it's increasing, decreasing, concave up, concave down. I'm going to find the coordinates of the endpoints, and I am going to show what the graph would look like. The graphs may be a little bit different from the graphs I've shown in the Google form, because if I graphed some of these, especially for B, it would get to be too small for you to see it, some of the things you needed to see. So I'd mostly just focus my attention on the graphs on the Google form to show where the critical points and inflection points would be seen, and not so much where the endpoints would be. These graphs here, I'm going to show that a little bit more where the endpoints are going to be as well, but it shouldn't be vastly different than the graphs you saw on the Google form. So So the first thing I'm going to do here is I'm going to calculate the first derivative. So the derivative of f of x is 3x squared minus 18x minus 21. And I'm going to use this to find any potential critical points and also to find out where this graph of f of x is increasing and decreasing, and also be able to use that to identify anything as a relative maximum or a relative min. So I set it equal to 0. I start simplifying a bit. Now, whether you want to use the quadratic formula or not, you can. This does factor. And so x equals 7 and x equals -1 are the two x values where I could potentially have critical points. So now I'm going to do a sine graph, signage graph or signage chart. So I just make a little number line. I put -1 and 7 on this. And I'm going to see what happens around there as far as the first derivative goes. So I'm going to pick some numbers. I picked -2 to be to the left, and when I plug -2 into f prime of x, I got a +9, so it's positive. Between -1 and 7 is 0. When I plug 0 into f prime, and that should be a prime there. I don't put the prime on all of these. It should be a prime. That should be a prime. F prime of 0 should be -7, so that's negative, and f prime of 8 was 9 again, so that should be positive. So I know several things here. I know that this graph is increasing from -5 to -1, and then again from 7 to 9. And again, I'm ending there because that's where, the endpoints are. It's decreasing between -1 and 7. So since I do have a change from increasing to decreasing at -1, I know that is a relative maximum at -1. So I took -1, plugged it into f of x, not f prime of x, f of x. So a little note here. F of 1, or -1, was 200. F of 7 was a -56. And that's how I calculated those y values. So I know it was a relative maximum at -1, 200. I know it was a relative minimum at 7, -56. Now that I've had the critical points, and I know where I have, maximums and minimums and where it's increasing and decreasing, I now take the second derivative and get 6x minus 18 and I set that equal to 0. And I solve for x, and I get that x equals 3. So x equals 3 is where I would potentially have an inflection point. Even though I'm saying it is there, it's still tentative until I actually do this sign chart. So the only number I'm putting on this number line is 3. Technically, I should probably put the endpoints -5 and 9 on there, but that's not as important. So at the second derivative, I plug 0 in, I get -18, which indicates that that's negative, which means it's concave down before 3. And if I put in 4 in the second derivative, I get 6, which is positive, which indicates it's concave up. So I do have an inflection point at 372. Again, this was the result of me doing f of 3, not f prime, f double prime. So my inflection point is at 372. It's concave up on the interval from 3 to 9. It's concave down on the interval from -5 to 3. Excuse me. So the information I've gathered so far, I've gathered where f of x is increasing and decreasing, where the relative maximum and the relative minimum are. I've also gathered where it's concave up, concave down, and where the inflection point would be. And I should also figure out where the endpoints would go. And again, each one of these was calculated by plugging them into f. So this was f of -5. This was f of 9. So I now have, aside from knowing the behavior, I do have 1, 2, 3, 4, 5 points. But you might think, well, 5 points is not going to give me a whole lot of information, but these are really important 5 points. It's where it starts and ends, where it's reaching a relative high point, a relative low point, and where it's going from a concave down to concave up. So the graph that fits all these characteristics looks like this. So that's what the graph would look like as a result, and it would fit all these categories here. For B, you were given this function here. This one's going to be a little tougher because it is a fourth degree polynomial, and whenever you go to do the first derivative, I would get 12x cubed minus 48x squared minus 132x plus 360. So that equal to 0. These are not easy. Polynomial equations are not easily solved. I mean, if you want to help at this point, if you get a situation like this, you want to use your calculator to aid you in solving these equations, go right ahead. That's what you should be using it for, not necessarily to calculate derivatives and what all. I happen to know because I set it up that it factors into 12 times x plus 3, x minus 2, x minus 5. Again, that's the way I set it up. So negative 3, 2, and 5 are the values of x are going to make f prime of x equal to 0. So these are potential critical points. You can do that through exploration, graphing techniques. If you have a calculator that does have a solver on it, you can certainly use that. So negative 3, 2, and 5 are what ends up on my number line. And again, I mean, I'm going to pick, x values that lie on one side or the other or between any of these critical points to calculate what's going on for f of x between them. So a lot of things going on here. So f prime of negative 4 was a negative 648, which of course is negative. So that means that f of x is decreasing before I hit negative 3. And then since f prime of 0, and again, I missed some primes here. Since f prime of 0 is 360, that's positive. I went from decreasing to increasing. So at negative 3, I do have a relative minimum. So you see here I did calculate the y-coordinate for that. At 2, I do have a relative maximum because I go from increasing. And then when I calculate f prime of 3, I got a negative 144, which indicates it's a decreasing at that point. So that is a relative maximum at 2, 476. And then, I plugged in a value that's more than 5. So I chose 6 and plugged that into f prime. I got 432, which is positive. So it goes back to increasing. So I have another relative minimum there. I also calculated the endpoints where those y values are going to be. And I use these plus and minus signs and the fact that I've already interpreted as increasing and decreasing to give my intervals of increase and decrease. So f of x is increasing when x goes from negative 3 to 2 or from 5 to 8. It's decreasing when x is going from negative 6 to negative 3 or from 2 to 5. Now I'm going to look for the inflection points. So starting with the first derivative, I'm going to now find the second derivative by just doing a derivative of the first derivative. So the second derivative is 36x squared minus 96x minus 132. I'm going to set that equal to 0. This is quadratic. Now again, I'm going to show it factoring into 3x minus 11 times x plus 1. Well, first I divide everything by 12 to make it a little easier. But again, I'm going to get the two values, x equals negative 1 or x equals 11 thirds. So inflection points are going to be, or at this point possibly be, at x equals negative 1 and x equals 4 thirds. So I'm going to set up one of these sign charts again and see what in fact really does go on. So I'm going to pick values before negative 1, between negative 1 and 11 thirds, and something after 11 thirds, which I'm going to plug into the second derivative to see what happens. So when I do the second derivative of f of negative 2, f double prime of negative 2, I get 17. That's positive, which means before negative 1, this graph is going to be concave up. When I plug into 0 into the second derivative, I get negative 11, which indicates that's going to be concave down between negative 1 and 11 thirds. And after 11 thirds, I pick the number 4. And f double prime of 4 is 5. That's a positive value, which indicates again that I'm going to expect to have something that's concave up. So here are my intervals of concavity. Concave up from -6 to -1, and then again from 11/3 to 8. Concave down between -1 and 11/3. And the inflection points, I have one at -1, -307, and again these two, and this should be 11/3. 286.19. These two y values were calculated by plugging their respective x values into f of x. So this is f of -1. This is f of 11/3. So you see you're plugging values into f of x, f prime of x, and f double prime of x, but you have to make sure you're plugging them into the right one of those for whatever it is you're looking for. If you're looking for a coordinate, a y coordinate namely, you're going to plug it into f of x. If you're looking for a value that's going to help you determine increase or decrease, that's going to be plugged into f prime. If I'm looking for a value that I'm going to plug in to find out if it's concave up or concave down, I'm going to plug that into f double prime. So the information I gathered on this function, that's where it's increasing, decreasing, the relative maximum, the two relative minima, the endpoints, the inflection points. Now, of course, some of the key information are these points right here. These are all coordinates that I can use to graph it. The other things help me more or less shape the graph, know if I'm bottoming up, topping out, which way I should be curling the graph, those sort of things. So it also helps me figure out, like, how far to the left I need my graph to go, how far to the right I need my graph to go, how far up and down I need to go. I mean, the first part was answered like this. That's how far left and right. But I can see that my y values had to go at least from -899 all the way up to, like, 2,908, which is the highest y value I see there. So, this helps me scale my graph so I can see what's going on. So, and that's what the graph would look like with all the points of reference on there. So that's the end of this example here, and your turn. I'm now going to do one more example where I'm just going to show you how to do some of this similar stuff with a rational function, and then it's going to be up to you to do some practice problems that we'll go over in class time. So if you have any further questions, please make sure to bring them up when we meet together. Otherwise, I'll see you in the next example. For example 2 here, we could actually use some of the same procedures that I just got done talking about in example 1 with polynomial functions. We could do some of the same things with rational functions. And in actuality, any other function that's out there. We just haven't really gone too far into other types of functions at this point. We've mostly dealt with, polynomial type functions like quadratics and linears and an occasional cubic and whatnot. And we've also talked a little bit about rational functions, and because we did those for limits and things like that. But we're going to kind of talk about this more in more detail, how I can use these first and second derivative tests and things like that. The only thing I have to make sure that I'm aware of as I do this is that any domain restriction, basically anything that could potentially be a vertical asymptote in particular, but also the holes as well. When I set up my sign charts, like I did in the previous example, I'm going to make sure that those get placed on my number lines as well, because oftentimes I could go from having an instance where I'm increasing to decreasing at around a vertical asymptote, but not necessarily it reaching a maximum, or it can have a change in concavity. As you can see here, here's a prime example of the graph next there. You can see, like, at the vertical asymptote x equals 2, that it's decreasing all the way through, because you can see as I go from left to right, it's moving in a downward direction. So I would expect to see for that graph there that the first derivative would tend to be negative throughout, everywhere, on the domain. But I can see that but I do go from concave down to concave up. So, although it's not an inflection point because x equaling 2 is impossible for this function, this vertical asymptote can act like, it can be a place where there is a change of inflection around it. So that's why it's important for me to put those points on there, because it's going to help me know if I have a change from increase to decrease around a vertical asymptote, if I go from a change in concavity from concave down to concave up or vice versa, and things like that. But we're also going to use limits a lot in here to find other things like this, and to better define some of these things, like the vertical asymptote, so I know how it's behaving around there, how, where I'm going to find the horizontal asymptotes, things like that. So if the polynomial in the denominator is 0 at x equals c, by continuity, it will be near 0 for x values near c, and reciprocals of numbers near 0. So basically, a rational function, p of x over q of x, has a vertical asymptote at x equals c if q of c, that means that basically if the denominator equals 0, as long as the top doesn't equal 0. So basically, a horizontal asymptote occurs where, x is approaching infinity and or negative infinity. So that's what I usually use. I do limits to find out about those. This goes more into negative asymptotes. And it kind of gets into the same idea we talked about already and we've made use of when we were looking at evaluating limits dealing with infinity here. This is where your books actually goes through more of the detail that I've already kind of provided to you. But essentially, when I have x approaching infinity or a negative infinity, that's why I divide both the numerator and denominator by the highest power of x, so I can get that to work correctly and to produce what I need to produce for that, so I can get those zeros to occur, and I know what the horizontal asymptote will be and where it's located. So I'm going to look at this function here. We're going to kind of walk our ways through each one of these so we can sketch a graph of what this function will look like. But we're going to look for all vertical and horizontal asymptotes as well as holes, and we're going to be able to identify those with limits. We want to find any intervals of increase and decrease, and then we're going to use the first derivative for that. Final coordinates of relative extremum. If there's any maximums or minimums, any place where it tops out or bottoms out, we're going to look for that as well. We're looking for intervals of concavity as well as any inflection points if there are any. We're also going to look for x-intercepts, because oftentimes with these type of graphs, you still needed some points of reference to help locate certain things. And then we're going to use all these things to graph the function, and those points will be more than enough to get a pretty accurate graph from it. So let's break down each one of these points individually. So I'm going to find vertical and horizontal asymptotes as well as the holes. So I first noticed that, the top and bottom do factor. And I can see here that, the top factors into 3x plus 1 times x minus 2. The bottom factors into x plus 4 times x minus 2. And I already see some things that, kind of we made use of in the past lessons to, help me figure out where some of these limits are going to equal each other, or where it's going to occur with them. So my domain restrictions are that x equals -4 and x equals 2, because those are the values of x that are going to make the denominator equal to 0. When I do the limit as x approaches -4 of f of x, I get 66 over 0. That indicates to me that I'm going to expect to see a vertical asymptote. So I already know what the vertical asymptote is going to do. Now, whether this limit's going to go, whether this limit, this two-side limit, is going to go to infinity or negative infinity, or if it's just not going to exist, in either case of those, I'm going to have a vertical asymptote there because of, getting a non-zero number over 0. I still want to know what the graph behavior is around there, because that's going to help me know also how to draw it. So when I do the limit as x approaches -4 from the right, I do get a positive value in the denominator, which means this thing would approach infinity. And I'm looking at the entire function. I mean, I could have also canceled these out, and I do it at some other point, but I'm not doing that for this instance here. I am keeping those in there to keep that 66 on top. So when I do the approaching -4 from the left, I get it's going from negative infinity. So that helps me know that, you know, when I eventually do this graph, and I'm going to kind of sketch it up here, if I can get this thing to work. Here we go. Come on, pencil. There we go. Oh, sorry. Um, at -4, you know, I'm going to see a vertical asymptote there. Now, I don't know, you know, where the axes are or anything like that, but I know from the left-hand side, the graph's going to tend to do something along the lines of this. And on the right-hand side, it's going to tend to do something along the lines. Now, I don't know about the concavity being right or anything like that. I don't know if it's going to do any turnarounds or things like that on the other else, but I at least kind of get that part. So I know the limit doesn't exist, but all of this information does tell me I have a vertical asymptote, and that's at x equals -4. I also test at x approaching the other domain restriction. But here I get a 0 over 0, which means I have more work to do. And since I've already factored it beforehand, I know that the limit as x approaches 2 of f of x is going to be equal to the limit of, as x approaches 2, of 3x plus 1 over x plus 4, which is basically the same function with the x minus 2's canceled out. And when I do that, I do get 7/6. And since it's now a number, that means that, you know, the limit as x approaches 2 of the original function is 7/6. It's just that, you know, f of 2 itself doesn't exist. And that's the indication that I do have a hole at that graph at 2, 7/6. So there's my hole. And then as far as the horizontal asymptotes go, I'm going to, as x approaches either infinity or negative infinity, what you see there is I've taken already the numerator and denominator and divided by the highest power of x, which is x squared. And I evaluated it, you know, all those things over an x squared becomes 0, so I do get 3. So y equals 3 is the horizontal asymptote. So B, intervals of increase and decrease. Now, I'm noting here that f of x is approximately equal to 3x plus 1 over x plus 4. The reason why I'm doing that is because since derivatives involve limits, the limits would have canceled out the x minus 2's anyway. I am safe at this point when doing derivatives, because I know I'm going to use the first derivative for this, to, you know, write the function and use this to evaluate whether it's increasing or decreasing or what have you, and to find any potential critical points. So when I do the first derivative, I do get 11 over x plus 4 squared once everything has been simplified. You know, as you see, I did use the quotient rule. I did simplify, and I get 11 over x plus 4 squared, which can never possibly equal 0. I cannot take 11 divided by anything to get 0. So as a result of that, I don't really have no potential critical points, but I should still set up a sign chart, and that sign chart is going to be set up with the x values that were my domain restrictions. So x equals -4 and x equals 2 is where I'm going to set up my sign chart. I don't know why the x equals didn't show up there. And I'm going to test points around this. I mean, because I'm still going to test it. So I'm going to do f prime of a number before -4, f prime of a number between -4 and 2, and f prime of a number after 2. I know that 2 is where the hole occurs, and usually there's not much change in increasing or decreasing, or even for that matter later concavity around where a hole occurs. But, you know, just to kind of note here that x equals 2 is also not in the domain is why it's on here. So when I pick some values in each one of those regions, when I do f prime of -5, I get positive 11, and that's positive. So that's going to tell me that, you know, And no matter what I put in there, actually, since 11 is a positive number, when I square a number, it's a positive number. This is always going to be positive. This tells me that this thing is increasing throughout its entire domain, from negative infinity to negative 4, and then again from negative 4 to 2, and then from 2 to infinity, excluding, of course, those points, but those points are not in the domain. Now I'm going to move on to the second derivative. Oh, let's first the extremum. Because f of x is increasing throughout its domain, there are no relative minimum or relative maximum points. So, intervals of concavity and inflection points. So I'll do the second derivative. I took the first derivative first and made it a little bit more simple. I'm going to use the chain rule and the constant multiple property and things like that to do a second derivative rather than go back to using the quotient rule again. So the second derivative is going to be negative 22 times x plus 4 to the negative 3, which becomes negative 22 over the quantity x plus 4 cubed. So again, this thing is not going to equal 0 either, so there are no inflection points. So I'm still going to test out these domain restriction values and place them on my number line, and I'm going to see what goes on for the sign chart for the second derivative. So if I pick a value that's less than negative 4, one between negative 4 and 2, and one that's after 2, I get these results. At negative 5, the second derivative is 22, which is positive, so it's concave up there. At 0, it became a negative 22 thirds, so that is negative, so it's concave down between negative 4 and 2, as well as after 2. The x-intercepts, all I'm going to be doing is setting this equal to 0, essentially. But again, I'm going to just look at the simplified version of this. And really, the only number that's going to cause me to have an x-intercept is what's going to make my numerator 3x plus 1 equaling 0. And it means that x equals negative 1/3 is going to be the value of x, where I'm going to have an x-intercept. So that point's going to be at negative 1/3, comma 0. So sketch a graph of the function. Again, I'm going to take all the information I gathered. I had a vertical asymptote at x equals negative 4, a horizontal asymptote at y equals 3. I have a hole at 2, 7/6, which is like 1 1/6. It's increasing throughout its entire domain. It's concave up before negative 4. It's concave down essentially after negative 4, with the exception that 2, where it's a hole there. There are no critical or inflection points. And I do have an x-intercept at negative 1/3, 0. So when I graph this, the main points of interest I can see there, negative 1/3, 0, 2, 7/6. There might be some other points I might want to try out as well, but that's generally what the graph will look like. And I'm not going to have you do anything, interactive with this. It's basically, at this point, it's a good time for you to start practicing this, so it's time for you to start your practice problems. So if you have any questions, bring them up in class. Until then, have a good day, everyone.